Hi everyone, welcome to the first video for Module 9 of Kines 7103, which is taught in the Department of Health, Kinesiology, and Recreation here at the University of Utah. In this module, we're going to be talking about models with multiple categorical predictors, and specifically in situations where we are crossing these factors. So we're going to have different categorical variables in our model, right? And we're going to look at the effects of each variable and then how those effects potentially interact with each other. So this is what we would refer to as a factorial ANOVA, because we have sets of different categorical factors and we want to conduct an analysis of variance, right, to understand which models give us the smallest sum of squared errors and what the individual contributions of each of these factors is. So for factorial designs, right, the idea is that we have one level of a categorical variable combined with every other level of another categorical variable, right? So if we, in sort of an abstract case, we have factor A and we have factor B. Factor A has two levels, right, A1 and A2. Factor B has three levels, B1, B2, and B3. If we cross these factors, right, so we have each level of B at each level of A. We have 6 total levels in our analysis, right? We have A1, B1, A1, B2, A1, B3, and so on. So in a fully factorial design, every level of one variable is represented at every level of another variable. So we can put this in like slightly more concrete terms if we think about perhaps an intervention that crosses two treatments. So we might have an exercise intervention in which we're looking at protein supplementation, carbohydrate supplementation compared to a control diet, crossed with different levels of exercise over, let's say, like a 6-week period. This effectively creates 6 different groups, right? We have a control group, and then we have a control group who did low exercise, a control group who did medium exercise, and a control group who did high exercise. We balance that against a carbohydrate supplementation group who did low levels of exercise, a carb group who did medium levels of exercise, and a carb group who did high levels of exercise to create 6 total groups when we cross these two factors. So we could analyze this using the ANOVA tools that we have previously used. So for instance, when we did a one-way ANOVA, we talked about a single categorical predictor that might have multiple levels. Now, we could treat this as a single categorical predictor, and we'll show in a moment why that's incorrect, but we could do it, right? So if we treat this as a one-way ANOVA, we could just treat these as 6 independent groups, for which we would then need 5 different codes, because you'll remember we need codes equal to k minus 1, where k is the number of groups. So we could get codes that accurately predict the mean of these 6 groups if we have 5 different orthogonal codes. So mathematically, this is going to work, right? Because we have contrasts. The sum across all the columns in each row is 0. And furthermore, all these contrasts are orthogonal, which is to say they're not going to be correlated with each other. And we can test that they're orthogonal by taking the sum of all of the cross products, right? So we take individual pairs of cross products, for instance, lambda 1 and lambda 2. We add their cross products together, those sum to 0. We'll kind of condense this and then just also look at lambda 4 compared to lambda 5, right? But if you summed any pair of cross products, the sum of the cross products is going to equal 0 in this coding scheme. So this would be an effective set of orthogonal contrast codes by which we could analyze these data. However, a one-way ANOVA treating all 6 groups as a single categorical factor ignores related families of treatments, right? We are assuming that then these groups aren't related to each other when we do that 6-level analysis. But in reality, these groups actually have something in common. They were all control groups, right? And these groups all have something in common. They were all carbohydrate groups. So if we wanted to be able to say, was there an effect of diet on average, right, we would actually want to pool the data from these groups with the data from these groups in order to make a comparison between all of the participants on this side of the table and all the participants on this side of the table in order to say, was there an effect of diet on average? Similarly, if we did this analysis with all 6 levels, right, we would be ignoring the fact that some of these groups are related based on how much they exercise, right? So this group and this group both had low levels of exercise, although they differed in their diet. This group and this group both had medium levels of exercise, and this group both had high levels of exercise. So if I wanted to ask, is there an effect of exercise on average, I would ignore the effects of diet and average these groups together, and average these groups together in order to say, all right, for people who got low exercise versus medium exercise versus high exercise, how did that influence the outcomes in my study? And finally, we can ask the more complicated question of, does the effect of diet depend on the level of exercise that you receive? Which is to say, for everyone on this half of the table, right, everyone in the control groups, we might see a certain pattern as we go from low to medium to high levels of exercise. Whereas for everyone in this half of the table, we might see a different pattern as we go from low to medium to high levels of exercise. So we actually want to know, does the effect of exercise depend on your diet? Or conversely, does the effect of diet depend on the type of exercise that you're doing? Those would be equally valid ways of interpreting this interaction between our two different factors. Now, in theory, yes, we could answer all of these questions through specific paired comparisons following our omnibus F test, right? So again, if we just looked at this as 6 independent groups, we could ultimately answer all of those questions, but we would need to compare a lot of different groups, and we're going to run a lot of different comparisons, which ultimately is going to increase our false positive rate. If we take this to an extreme example, for instance, if we wanted to exhaustively compare all of these groups, that's going to require 21 comparisons, because one gets compared to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 2 to 3, 2 to 4, 2 to 5, 2 to 6, 3 to 4, 3 to 5, so on and so forth, until you get 21 different paired comparisons that you have to run. If in each of those comparisons our alpha level is set to 0.05, right, or a 5% chance of a false positive, that means now as a set, we're above 1. So a false positive is not just likely among those 21 tests, it's actually expected. We've run enough tests that we are almost guaranteeing ourselves to get a false positive if we do all of those different comparisons exhaustively. So instead, we can actually create contrast codes more intelligently and build families of related tests, right? So by using specific sets of contrast codes, we can actually answer our hypotheses more directly and better control the false positive rate for a given family of tests. So what we're going to do next is create contrast codes that account for the different groupings within our data. So we're going to create one contrast code for our diet, we're going to create a set of contrast codes for exercise, and we're going to create a set of contrast codes for the interaction. So in order to create a contrast code for the main effect of diet, that's relatively easy because diet only has 2 levels, so we need k-1 codes, right, or 1 contrast code for the effect of diet. So lambda 1, for which codes which diet group you were in, has 2 levels, -1 if you were in the control group, and 1 if you were in the carbohydrate group. And as you can see, if we sum across the columns within a row, right, this is going to be a contrast because that sums to 0. Similarly now, we can get the main effect of exercise. Now exercise has 3 groups, so we need 2 contrast codes in order to represent that appropriately. So we're going to create lambda 2 and lambda 3. In lambda 2, we're going to use the -1, 0, and 1 coding scheme that we've used before. But now notice that this is following what level of exercise you're doing. So both the low control group and the low carbohydrate group get a -1 because those are both low exercise groups. The medium control and the medium carbohydrate group both get a 0 because those are both medium exercise groups. And the high control and the high carbohydrate group both get a +1 because those are both high exercise groups. So lambda 2 is coding exercise. It ignores diet completely. Similarly with lambda 3, right, this is our quadratic contrast to pair with the linear contrast we made in lambda 2, but we're coding low and high exercise groups as -1 and medium exercise groups as 2, and we're doing that regardless of which diet group that you got. So as a set, these 2 contrast codes tell us what level of exercise you had, but they ignore what kind of diet that you got. In order to answer the question about the interaction, what we do is we multiply the interacting variables together. So this is the same as what we've done with interaction in continuous regression. The only difference is that now we're going to have to multiply individual contrasts together when we have more than one contrast per variable. So for the effect of diet, that's not too hard because we have just one contrast, right? We have lambda 1. But in order to create the codes we need for the interaction, we're going to have to multiply lambda 1 by lambda 2 to create lambda 4. And we're going to have to create a contrast of lambda 1 times lambda 3 to create lambda 5. Right? So our interaction is also going to take 2 contrasts because we had 2 for the main effect of exercise times 1 for the main effect of diet. Had we had more levels of diet, the interaction term is going to get bigger and bigger because we're going to need more and more contrast to accommodate that. But as it is, right, you can follow the multiplication here for lambda 4. We're taking lambda 1 times lambda 2 is 1. Lambda 1 times lambda 2 is 0. Right? Lambda 1 times lambda 2 is negative 1. And then when we switch over to the other group now, notice that the direction of this coding changes. So we have lambda 1 times lambda 2 is negative 1. Lambda 1 times lambda 2 is 0. And lambda 1 times lambda 1 is positive 1. So now lambda 4 is still a contrast, but you'll notice that when we have the control group, low exercise is coded as 1, high exercise is coded as negative 1. Whereas when we have the carbohydrate group, low exercise is coded as negative 1 and high exercise is coded as positive 1. So if we've built these contrasts correctly, what this interaction term is going to allow us to test is how the effect of exercise changes whether we're in the control group or if we're in the carbohydrate group, because now the variables are being represented opposite to their values in the previous contrast. And similarly with lambda 5, right, we're multiplying lambda 1 times lambda 3, so negative 1 times negative 1 is 1, negative 1 times 2 is negative 2, and negative 1 times negative 1 is positive 1, and then the sign of these three values switches when we go into the other group. So these contrasts, right, in which the sign changes as you go from one level of a variable to the other level of the variable, is what's going to allow us to see, is the effect of exercise different if we have different diets. Now, we have to also check to make sure that these are orthogonal contrasts, right? So you can note that these are contrasts because if we sum each row across the columns, it's going to be 0. And these are orthogonal, which is to say they are uncorrelated, because the sum of the cross products is 0. And again, we can just pull out some of the cross products here. So for instance, lambda 2 times lambda 3, right? We have that if we take the cross products, multiplying each of those terms, add them all up, that sums to 0. Lambda 4 times lambda 5, multiply each of those terms, add them all up, and then that's going to sum to 0. We don't need to do this for lambda 1, of course, because for diet, there's only one level. All right, so now that we have all of our different contrasts in place, we can ask several different questions that we're interested in order to test the effects of both diet and exercise in our study. So the first thing that we'll get is an omnibus F-test for the full model. And that's going to tell us how much variance in the dependent variable was explained by all of our predictors as a set. Right? So for the omnibus F-test of our full model, we're comparing a model A in which we have parameters for the intercept, the effect of diet, the first contrast for exercise, the second contrast for exercise, and then the two interactions. So we ultimately have 1, 2, 3, 4, 5, 6 betas that we're estimating here. And we're comparing that against a model C in which we're estimating just a beta 0. And so we could write this either explicitly stating that we're saying there's no effect of diet, no effect of exercise, and no interaction, or we could just omit those values from the model entirely and just write the model C as y is equal to beta 0 plus error. In either case, we're comparing a model A with 6 parameters to a model C with 1, so the degrees of freedom for the F-test of the full model would be 5 degrees of freedom, because it's parameters in model A minus the parameters in model C gives us the first degree of freedom, or the numerator degrees of freedom, for the F-test. Now, we can dig a little deeper though, right? Because again, that omnibus F doesn't actually tell us which variables are doing the work in our model. It just tells us how all of our variables are functioning together as a set. So if we wanted to say, for instance, what is the main effect of diet? Or on average, was there an effect of diet? We're going to compare the same model A as in the full model, right? So a model with all our parameters to a model C in which it's everything except the effect of diet, right? So we omit that effect / we set the beta to 0 in model C. So we don't allow diet to have any influence on its own. And therefore the degrees of freedom here are going to be 1 because we have one more parameter in model A than we do in model C. And if we compared these two models, right, we get the sums of squared errors in model A, we get the sums of squared errors in model C. We use that to calculate a proportional reduction in error, which we can turn into an F observed, and then we can calculate the p-value. That will allow us to say, was there a statistically interesting effect of diet given the null hypothesis? We can do the same thing for the effect of exercise, but it gets a little more complicated because, of course, exercise is being represented by two different contrasts. But the omnibus F for the main effect of exercise is asking a similar question. On average, which is to say ignoring diet, was there a main effect of exercise? Now note that because exercise had 3 levels, the omnibus test requires removing both contrasts, right? So we're going to have a model A, again, that has everything in it, compared to a model C, in which we set the coefficients for those contrasts to 0, or the other way to write it would be that we ignore those contrasts in the model completely. In either case, we're not allowing exercise to have any influence on our model's predictions, and we would calculate the sum of squared errors for this model compared to the sum of squared errors for this model. We do a model comparison, and we'd get an F statistic. And in this case, the numerator degrees of freedom for this test would be 2, because the main effect of exercise has 2 additional parameters beyond the model C that we used to test it. Finally, we can also get an omnibus F test for the interaction of diet and exercise. And this is what's going to allow us to say, did the effect of diet depend on exercise, or did the effect of exercise depend on diet? Either of those is a valid way of looking at the interaction. Now note that this interaction requires multiplying the interaction factors by each other, right? So as we did when we were setting up our contrasts. So in this case, it takes 2 times 1, or 2 contrasts, in order to test this interaction. Because our main effect of exercise, right, has 2 contrasts. So our interaction is going to be x1 times x2 to get x4, and x1 times x3 to get x5. So when we want to test the interaction, we're going to have to remove two coefficients from our model. So we're comparing a model A with everything in it to a model C where we're either forcing those coefficients to be 0, or we could write it just ignoring those coefficients altogether. Either way, right, it has the same effect on what our model actually estimates. And then again, we'd get the sum of squared errors for model A, sum of squared errors for model C, calculate the proportional reduction in error, convert that to an F statistic, and then we could do a model comparison, and the numerator degrees of freedom for this F observed would be 2, because there are 2 more parameters in model A than there are in model C. So we're going to get a little more practice doing this in the lab, but in the next video I really want to focus on how we can sort of interpret these interactions and really start to think conceptually about what the difference is between interactions and main effects. So we're going to simplify things a little bit in the next video to just look at a 2x2 design, right, where we've got a factor A that has 2 levels and a factor B that has 2 levels, but we just want to get a little bit of practice thinking about what does a main effect really mean, what does an interaction really mean, and how should I interpret those before we move on to some of the other more complicated details about model fitting and estimation when we have a multifactorial model.